This conference will now be recorded.
Hello everyone. So we were discussing from the last class classification of acids, and we will continue with classification of acid. After that there will be classification of bases, and based on this we will discuss some problems. Whatever topics we have finished in the last class, based on that we will discuss some problems, and after that we will discuss, if time permits, the preparation methods of acid and bases and their chemical properties. So here we have the classification of acid, which is on the basis of strength. So there are different ways you can do classification of acid, and here we are doing the same thing, but now it is on the basis of strength. So there is strong acid and there is weak acid, two types of acid. So strong acid, as you can see, definitions we have seen in the last class, that is finished, but now you can see some examples for strong acid like HCl, HNO3. Now these are very common, the first three are very common, but there are some other strong acid that also we should know: hydrobromic acid, hydroiodic acid, perchloric acid, chloric acid. So in strong acid, what happens? Suppose we have started with X moles of acid, then what will happen? All these X moles of acid will be dissociated. So if I am saying that I have taken X moles of HCl, so there will be formation of X moles of H plus and X moles of Cl minus. That means all the molecules will be dissociated. So you can say out of 100 molecules, 99 will be dissociated, which is close to 100%. So in terms of mole also, we can say when you are starting with X moles of HCl, there will be formation of X moles of cation H plus and X moles of Cl minus. But when it is weak acid, for example, here we have sulfurous acid, which is H2SO3. Look at the difference in the formula. Sulfuric acid is H2SO4, this is H2SO3. Then we have oxalic acid. This is basically organic acid. Oxalic acid is 2CO2H group like this. So the formula is written in this way: C2, this side O2H, this side O2H. So this is the formula for oxalic acid. Then H2PO4, HNO2, nitrous acid. Benzoic acid, this is also organic acid. Acetic acid, this is also considered under organic acid. Formic acid also organic acid. Though the use of acetic acid, the discussion related to acetic acid, it is very common under inorganic chemistry. So what is the difference with that is between strong acid and weak acid? So when it is weak acid, suppose I am starting with X moles of any weak acid. Suppose I have started X moles of HNO2. Now out of this X, only some few percentage will be dissociated. Now if you are thinking what is this percentage, that will vary depending on what type of acid you have taken. Suppose 10% or 2% or 5% of X, that is dissociated. So it is not that all the molecules present in X moles of HNO2 that will be dissociated to H plus, and the anion is nitrite ion NO2 minus. So that is the difference with that is the difference between strong acid and weak acid. That is how much is the, that is what is the percentage of dissociation? Is it 100% or is it 10%, 20% like this? Now this 10, 20 or 2% or 1%, that depends on which weak acid you have taken, but it is never close to 100. That is sure, because if it is close to 100, you will call it a strong acid, you will not call it weak acid, right? So next you will have, okay, so this important note here, you have to remember that in general mineral acids are strong acid. Okay, so we have seen the that is the classification of acid not on the basis of strength. Suppose on the basis of source, that we have seen in the last class. So when it is on the basis of source, whether it is generated from some minerals or some organic source, depending on that, we have two categories: mineral acid and organic acid. Now it is observed mostly, so as a note, this information is important, that mineral acids are shown to be mostly strong acid. Though remember that it is not always necessary, but mostly these type of observations are common. Okay, so organic acids are weak acid and mineral acids are strong acid. So this is the difference between mineral acid and organic. That is one more difference you can say. So most of the time organic acids are weak acid. So as you can see here, already you can see some organic acid, right? In this example, like oxalic acid, then benzoic acid, then formic acid, all these are basically under weak acid we are seeing here, but they are also they are also organic acid, right? So this is the classification of acid on the basis of strength. Next we will see the classification of bases. So just like acid, here also two different bases, that is two different ways on the basis of which we will do the classification. One is based on acidity and another one is based on strength. So the classification of bases, we will first see how it is on the basis of acidity. Remember, in case of acid, we have seen the classification based on basicity. Now the term is reversed. Now it is acidity. So when it is acidity, that is classification of bases on the basis of acidity, we have to know the definition of acidity of bases. So acidity of bases, the definition is the number of hydroxyl ions present. How many hydroxyl groups are present in the base? Depending on that, we will call that, okay, this base is having acidity 1 or 2 or 3, depending on how many OH minus group you have. So suppose I am saying monoacidic base. Example is NaOH, because from this NaOH you will get only one HO minus, right? Similarly, when you have taken CaOH whole 2, after dissociation, calcium is having charge Ca2 plus, and there will be formation of 2 OH minus. So this is diacidic because you have 2 OH group after dissociation. Though it is true that from the formula you can understand that there is 2 OH group, but still if you write the full structure, that it will be better, that is it will be help you to understand the dissociation. And when it is FeOH whole 3, it will be Fe3 plus and 3 OH minus. Okay, so in this way acidity of bases, depending on acidity of bases, we can have different types of base, right? Next we'll see classification of, sorry, it is base. Classification of base on the basis of strength. So just like acid, where you have seen classification of acid on the basis of strength, here also we can do classification of base on the basis of strength, and the logic is same. That is, suppose you have started with X moles of bases, what is the percentage? Is it close to 100%? Then you can call it strong base. If it is not, if it is 10%, 2%, 5%, you will call it weak base. So strong base, they are the bases almost completely ionized in water and release more hydroxyl ions upon ionization, or low concentration of hydroxyl ion. So it is high concentration. So when you have taken X moles of NaOH, then after dissociation there will be formation of sodium plus cation and HO minus anion. Now this will also be X moles and this will also be X moles, right? That means whatever is the amount you have started with, you will get exactly same number of moles of HO minus. Now if it is suppose diacidic, suppose instead of NaOH, if I have taken another strong base like CaOH whole 2, then double moles of HO minus, because per mole of CaOH whole 2 there will be formation of double amounts of OH minus, right? So here suppose you are solving some problem where you have to find the concentration of HO minus, and look at the formula that per mole how many OH minus generation possible. So if given concentration of CaOH whole 2, suppose it is given that 0.2 moles, so obviously the number of moles of OH minus will be 0.4 moles, it will be double. So strong base is 100% dissociation or almost completely ionized, that is complete ionization. But weak base is weakly ionized on dissolving in water and releases less number of hydroxyl ions upon ionization, or low concentration of hydroxyl ion. So now the concentration, it will be low. So similarly, just like any strong base, if you have started with a weak base like ammonium hydroxide, it will produce NH4 plus ion and OH minus ion. So if you have started with X moles, maybe or only, that is some few percentage, suppose I am saying 5%, that is 5 divided by 100, this number of moles, I am just arbitrarily saying, don't think that it is 5%. So suppose 5% or 2% of X of NH4 plus, and also because when NH4 is like this, HO minus, that is also same percentage. So you have started with this number of moles, but you will get HO minus only a few percentage. So that is weak base. Okay. Now we will solve problem. There will be equilibrium sign. So here a system is given. For the system shown here, HOBr plus OH minus, in the right hand side water and OBr minus. So if I am writing this once more, Bronsted would classify the base species as, so you can see total 5 options are there, and in each option there is a pair, right? That means in this pair both the species must be Bronsted base, then only you can select it as correct option. So HOBr, and there is HO minus ion. Now equilibrium, there is formation of water and OBr minus. Now OBr minus is generated from HOBr. It means what? This HO minus is capturing this proton. So if you ionize it, it will be something like this, H plus OBr minus. So this H plus is now combined with HO minus, and in the right hand side, this H plus and HO minus together is producing water, and the fate of HOBr is now it is OBr minus. Okay. So you have total 4 species are there. Left hand side you have HOBr and hydroxyl ion, 2 species, and right hand side you have 2 more species, water and 1 more anion. Now among these 4 species you have to recognize which species you can classify it as Bronsted base. So first of all you have to know what is Bronsted base definition. So according to the Bronsted theory, the base will be that species which can accept H plus. So Bronsted base means it can accept H plus, right? Now look at these molecules. Here left hand side HO minus is accepting H plus from HOBr. So I can call it Bronsted base. I'm writing it at BB. That means Bronsted base. In the right hand side, if you consider OBr minus and water, and suppose this is your reactant side and you are moving from this to this side. Now what is the reaction? Now as if OBr minus is capturing 1 proton from water. Water, if you consider its structure like this, then 1 H will be captured by OBr minus, and rest of the part that will be in the form of HO minus, which you are having in this side. Okay. So as there is equilibrium, you have to consider first the forward direction, as if HOBr and HO minus is your reactant and your products are H2 and OBr minus. Similarly, you also have to consider the backward direction, where OBr minus is capturing proton from water. That means this species is also capturing H plus. So I can call it Bronsted base. But what about the other 2 species? Why these 2 will not be considered Bronsted base? HOBr, what it is doing? HOBr is giving proton to HO minus. So it is basically Bronsted acid. It cannot be base. Similarly, if you consider the reverse reaction, water is supplying H plus to OBr minus. So it is proton donor, H plus donor. So it cannot be Bronsted base. So Bronsted base will be only 2 species, this one and this one. So that is why the middle option, that is C, that will be the correct option. If you look at the other options, option A, it is partially correct. It is having this species, but this is not correct. Both the species must be acting as Bronsted base. Then only you can select it as correct option. This one is also partially correct. This is partially correct and this is fully incorrect, right? So correct option is C. Again, we have an equation where equilibrium you have to consider. HF reacting with water, you are getting hydronium ion and fluoride ion, F minus. In this equation, you have to recognize the correct option. So look at the options, what it is saying. The first one is saying water base HF is conjugate acid, then acid conjugate base. So see, all the options are related to conjugate acid and base pair, right? So you just have to recognize the correct conjugate acid base pair. So in this case, consider the first option first. It is saying that H2O is a base. Fine. So if it is base, its corresponding, suppose I am writing water is base. Then the corresponding conjugate acid, it should be HO minus, because conjugate acid that differs with the base by a single proton. So HF cannot be the conjugate acid of water. So first option is not true. Come to the second one. It is saying H2O is an acid first. Fine. It is saying that H2O is acid. So its corresponding conjugate base, that should be, sorry, here I have by mistake written. If H2O is base, its corresponding conjugate acid, that will be, after accepting H3H plus, it will be H3O plus. Okay, this is the correct conjugate acid of H2O, because now H2O is acting as a base. So obviously it will accept H plus, not it will release H plus. But in the second case, H2O is, if you are calling H2O as an acid, now it should donate H plus. When it is donating H plus, it will be converted to HO minus species. Now these two are related to each other as H2O acid, conjugate base is hydroxyl ion. But here it is mentioned that H2O is an acid, HF is the conjugate base. But that is not true. It should differ only by a single proton. That is not present here. So that is why this is also incorrect. Third option is saying that HF is acid. So again, under acid category, I am writing HF. Now, if it is acid, it will donate some H plus and it will be converted to F minus. So F minus should be its conjugate base. And here it is mentioned that HF is acid and F minus is its conjugate base. So this is actually correct. Why the other options are not correct? Let's have a look. Let us have a look. HF is base. If HF is base, acting as a base, then H3O plus cannot be its conjugate acid. If HF is base, that means it should capture one more proton and it should be converted to species something like H2F plus, just like hydronium ion. But that is not mentioned in the question, so this cannot be true. Then the last option is saying that if HF is base, F minus is its conjugate acid. Fine. So I am writing HF as base. Let me write it here. Now, if it is base, it should capture proton. That is the same concept here. In the previous option also it is saying that it is base. Now, if it is base, it should capture some proton. It should be converted to H2F plus. It cannot be F minus. First of all, HF, it is not base. If it has to act as base, there must be some other species which is more acidic than HF. Then only it can act as base. Mostly HF is known as acid. It donates proton. It is converted to F minus. But suppose if I am saying HF is base, that is only possible if the other species with which it is reacting, this other species must be very strong acid, more strong than HF as acid. Then only HF can act as base to that species. But that is different thing. Here we are interested only to recognize the conjugate acid base pair. HF, if it, suppose HF is base, that is fine. But base means it should capture H plus. Then only it will be converted to its conjugate acid. But HF and H2O, these two are not related at all. So again, here the middle option is the correct option. Okay. We have two columns, column 1, column 2, and In column 1, there is mention of some strong and weak acid base. In column 2, we have some compound. So you have to recognize it. So first we have H2SO4. Now H2SO4, we know it is strong acid, right? It is strong acid. So 1 is matching with P. Now if P is matching with 1, that you can get in so many options. You can cancel out only this one. And the second one, that is CH3COOH. This is under the category of weak acid. That means 2 should match with Q. Now Q is matching with 2. That you can get only option A and B. So you can cancel this one. Next is NaOH. NaOH is strong base. That means 3 should be matching with S. Right? 3 is matching with S. That means here option A should be the correct option. And R only 1 is left. That means when it is NH4OH, it is weak base, and weak base, that is R. Fine. So comparing both sides, we have reached the correct option, which is the first option, right? We have another question here. Which of the following species compound is not a base? Four compounds are there. You have to recognize which one is not base. Now look at the first compound. It is aluminium hydroxide. And when it will dissociate in water, it will produce aluminium 3+. That is the only charge possible for aluminium. And there will be total 3 hydroxyl ion. So there is formation of hydroxyl ion. So it is considered as base. NaOH, you already know it is a base. We just have to recognize that species which is not a base. KOH is also just like NaOH, only difference is you have different metal. Instead of sodium, you have potassium. That is the only difference. But the last one, it is sodium chloride. When it will dissociate, you will get Na plus and Cl minus. It is not producing any hydroxyl ion. So if we consider the definition of Arrhenius, it cannot be, though here on which based on which theory we have to choose base, no theory name is mentioned. That is fine. But as here OH groups are present in most of the compounds, you can consider Arrhenius. Even if you consider the other theories, suppose if according to Arrhenius, sodium chloride should be our correct option because it is not producing any hydroxyl ion. Fine. Okay, now if you want to know Brown state base means what? Brown state means it should capture H+, but NaCl is neutral species. There is no tendency for NaCl to capture H+, so it is not Brown state base. Then what about the Lewis base? Lewis base is definition is it is electron donor, that is electron pair donor, or if there is some negative charge, that negative charge will be donated to some other electron deficient species. But that definition is also not fulfilled here because NaCl there is no tendency to donate any lone pair, right? So NaCl is basically a salt. Now what is salt? We have not discussed it, not yet. That is also part of this unit. Acid, base and salt. Total 3 species mainly, that is all about this unit. So salt is also in this unit, though that is not discussed. How salt is produced? Basically salt is produced when acid and base react together. Then we get salt. So if you are thinking that sodium chloride is produced from which acid and salt, so you can take NaOH as base, you can take HCl as acid. So when these two combine with each other, that is you have now acid, you have base. So this part, positive part and here the negative part, together it will make NaCl, which is the salt, and the remaining part together will make water. So acid base together it makes salt and water. That is as a definition of salt, you can say it is produced by combination of acid base. That we'll discuss later in this unit. But also in today's class, when we'll discuss the chemical properties of acid base, we will discuss this reaction between acid base. Then also you'll be able to understand salt once more. So here the last compound is not a base, and that should be our correct option. Now in this question, here until whatever you are seeing on the screen, it is the direction. That is the instruction based on which you will solve the problem. The problem is not yet appeared on the screen. Only the direction is given. So the direction is saying that in the following questions, which will appear after some time, a statement of assertion is followed by a statement of reason. So when the problem will appear, you will be seeing two statements in each problem. One statement is assertion and the second statement is reason. For each problem, there will be total 3 problems. Now, among these 4 options, A, B, C, D, which is applicable for all these 3 problems, you have to choose any of these options, either A, B, or C, or D. Okay. So the first A option is saying that both A and R. A means assertion. R means reason. So both A and R individually true. So when you will read the statements that will be present in the question, you have to recognize whether they are true or false. So the assertion statement and reason statement, if both are individually true, that is independently true, then we can say both A and R are individually true, and R is the correct explanation of A because it is the reason. It is the correct explanation of the assertion. So this is one condition possible. Second thing that is possible, both are again individually true, but it is not necessary that R will be the correct explanation of A. That is another possibility. The third possibility is the first statement is true, not the second one, and the last possibility is false and true. Though there are some other possibilities possible, that is both are true, both are false, but that is not present here. You just have to choose among these 4. So let's have a look to the first question, which is having 2 statements, obviously, as I have said. So the assertion statement is saying that acetic acid will not act as an acid in benzene solution. So benzene, mostly we are, whatever discussion we have done until now, mostly the solvent we have taken water. But there are some other solvent possible. So benzene is one such solvent, which is basically organic solvent. So when benzene is the solvent, or you can say general term, you can use non-aqueous solvent. There may be different types of solvent. Sometimes liquid ammonia is also acts as a solvent. So all these are, you can say, a broad term you can use non-aqueous solvent. That is except water. If you are using any other solvent, you can call it non-aqueous solvent. So when there is non-aqueous solvent, then acetic acid will not act as an acid in this non-aqueous solution. Now, is it true? Is it false? That we have to understand. And the second statement is benzene will not accept proton. Now, benzene is this type of molecule. So all these positions, there is carbons, total 6 carbons, and there will be 1 hydrogen. So total 6 hydrogens are there, right? But whatever it is, it is highly neutral compound. There is no tendency to accept proton under normal condition. So that is why the second statement is true. The first statement is also true, that acetic acid will not act as an acid. Now acetic acid is CH3COOH. If you take it in water, it will dissociate to CH3COO minus and H plus, right? But this type of dissociation is possible in water, but not possible in benzene. Now, if you are thinking why it is possible in water, so what happens? This H plus, which is dissociated, this H plus is actually captured by water. So better you can write this type of cation where water and proton together is making this hydronium ion. Basically, when we write the dissociation, simply you can write H plus and acetate ion, which is CH3COO minus. But if you are writing CH3COOH plus H2O, and in the right hand side you are writing H2O plus and CH3COO minus, that is also fine. So here water is helping its proton to, that is to break this OH bond. So water is acting here as a base, and this is acting as acid. So it is possible in water, but it is not possible in benzene solution because Benzene cannot capture this type of H plus that you are having for water. So the first statement is true. The second statement is also true. And see, the second statement is actually explaining why the first statement is actually true. The first statement is true. Why? Because benzene cannot accept proton just like water. So it is not just they are individually correct. The second statement is also the correct explanation on the first statement. So which option we will choose? We will choose A. So for the first question, A will be the correct option. Come to the second question. Assertion is saying ammonia is a base. Fine. It does not contain OH minus ions. Now, ammonia formula I have already written. And it is also true that there is no hydroxyl ion. So what I will say, it is true because ammonia can act as a base. It is true that there is no H minus ions. And according to Arrhenius, you will say that how it can be base. But that is not the only theory. We have two more theories also. So as ammonia can capture H plus, suppose you are having some source of H plus and then ammonia can capture this H plus. So it can capture proton and itself will be converted to NH4 plus cation. So according to Bronsted, it is a base. Similarly, if you apply Lewis theory, then also it is a base. Because according to Lewis, any species which can donate its electron pair, which is present over nitrogen, to some electron deficient species. So electron deficient species, very good example is BF3. So this lone pair will be donated to BF3 and ultimately it will be Lewis base. So from Arrhenius point of view, there is no H minus ion, but that doesn't mean it is not base. So individually they are true statements, but the second statement is not explaining the first statement. So you cannot say it is the correct explanation, right? So it should be option B. Individually they are true, but R is not the correct explanation of E. Okay. Last question. Assertion is saying that concentrated H2SO4 can be diluted by adding water dropwise to acid. So suppose you have taken some acid, H2SO4 you have taken, which is strong condition. There is no water. And you want to make dilute H2SO4. So you have to mix some water. But what should be the mixing process? Is it that H2SO4 is present in large quantity in any container and then you are adding dropwise water? Is it the correct way? Or there is another way, that is the reverse addition if I say. That is, you have taken a large quantity of water and now you are adding dropwise H2SO4. Concentrated H2SO4 you are adding so that you can make dilute H2SO4. Which is the correct way of the addition of water and H2SO4? Whether you will add water dropwise towards H2SO4 or dropwise H2SO4 addition to H2O in present in large quantity. Which one is correct way to make dilute H2SO4? This one is the correct way to make dilute H2SO4. Never try this one in the laboratory because it will lead to explosion. What happens? H2SO4 it is very water attracting species. Okay, so H2SO4 can draw a lot of water. So this tendency is very high. So when you will dropwise you will add water, there will be explosion because there is a huge amount of heat, energy is generated. So that is why there will be explosion. But if you do the reverse process, you have taken large quantity of water and very little amount of H2SO4 you are adding. That is the right way to do it to avoid accident, right? So assertion concentrated H2SO4 can be diluted by adding water dropwise to acid. This is not correct. This is false. Okay. And the second statement, concentrated H2SO4 has more affinity for water. It is true. Actually, see, if the opposite statement you have in the assertion, suppose I have here the statement concentrated H2SO4 can be diluted by adding concentrated H2SO4 dropwise to water. If the statement is reverse, then it will be true, not only true statement, then the second statement is also the correct explanation. In that case, option A will be right. But here the first option is already false. Second option is true. So you have to choose here option D. So here D will be the correct option. Because if you try to choose this one, A and R are not individually true. They are individually, one is true, another one is false, right? So A is false, R is true. You have to choose option D. So if you do not have any prior experience of how to do this assertion reason type of question, because in higher grade these type of questions are very common. So this question, when you'll be able to solve this type of problem, it is a very good practice, right? So A, B, D for the questions 1, 2, 3 respectively. Which of the following represent the correct order of acidic strength for equimolar aqueous solution of 4 species: HCl, H2SO4, NH4OH, NaOH. Correct order of acidic strength. So whatever order you are seeing here, suppose just choose the first order. H2SO4 is present on the right hand side extreme. So what it means? It means it will be the maximum strong acid, and at the other end we have HCl, so it will be the minimum strong acid. So gradually the strength is decreasing, and that is true for all the options. That is the meaning of this question. So you have to choose the correct order for acidic strength, max to min, right hand side to left hand side, and all are present equimolar, that is same moles of each of these species present, right? So first we will write all the species here. So HCl, it will dissociate to H plus and Cl minus. Then H2SO4, same number of moles. So suppose we have 1 mole of each of these species. Now you will have 2H plus, SO4 2 minus. Then the next species, NH4OH, NaOH. Now it is true that these two are not acid at all. They are actually bases, right? Now, why, if you are thinking why they are given in this type of question where you have to choose the acidic strength. See, it is true that they are bases. So what you will do? You will keep them at the lower end because they are not acid at all. And among these two bases, the base which is stronger, that you will keep at the last one, because among these two spaces, the base which is stronger, that will be, as I said, that will be weaker, right? So we know that in each for OH, here also you will get 1 HO minus, here also you will get 1 HO minus. But remember, though you have same moles of both, but the amount of OH minus, it will be full dissociation, but it will not be full dissociation because it is weak base. This is strong base. And these two are acid and both are strong. Then how we will understand that which one will be strong acidity? Remember, as you have taken equimolar amount, and here from 1 mole you are having only 1 mole of H plus. Both cases full dissociation, complete dissociation, 100% dissociation. So here from 1 mole you will get 2H plus. That means H2SO4 should be acting as a better acid compared to HCl. It should be at first position. Then it should be HCl. So acid part is complete. Now come to base. NaOH is more basic. That means it will be less acidic than NH4OH. So considering all this, it is not the correct option. It will be the last one. Sorry. It is not the correct option. This one is the correct option, the last one. Correct order of acidic strength. How it, the first option, how it can be correct option, because after H2SO4 it cannot be anyway. This is a mistake. Remember, the last option is the correct option. This is the maximum strong acid because you have taken equimolar, so you will get 2H plus, and number of H plus high means it is more acidic, and after that HCl. Now these two, though both are bases, but this is not so strong base, so you can keep, when you are arranging according to acidic strength, you can keep it before NaOH. Okay. Which of these species is probably the weakest acid? So here we have total 3 acids we have total, and these two are anion. Now if you observe carefully, these two anions are basically produced from H3PO4, isn't it? Right? Now this H3PO4, this is actually weak acid. Now in this H3PO4, we have to understand how many, though here from the formula you can see total 3 hydrogens, but whether all these hydrogens are that is, it is able to dissociate or not, that you have to understand. So first of all, we will write all the, that is HCl, you know, it is H plus and Cl minus, and it is not weak acid at all, right? Then H3P, I will come to this acid later. First, let me write the dissociation products of HNO3, which is H plus and HNO3 minus. Now come to H3PO4. So when it is H3PO4, the structure we have to understand first. Sometimes mere presence of 3 hydrogen or 2 hydrogen, it is not necessary that all of them will be able to dissociate. Though in this structure, luckily all these hydrogens are able to dissociate, and it depends on whether this hydrogen is attached to oxygen or not. It has to be attached to some electronegative atom. So there are some other phosphorus related acid where sometimes what will have, there will be pH bond, and these bonds are not dissociable. So this H will not be dissociating as H plus. That is not possible here. It is possible only if it is attached to. So all these 3 hydrogens, they are able to dissociate. So when there is fast dissociation happening, what you will get? You will get this type of species, OH, OH, and this species is equivalent to H2PO4 minus, which is present in option C. Similarly, if another H is removed from this species, you will now have H plus and HPO4 2 negative. Now negative charge will increase, which is present in option D. So if you are thinking which one will be weakest, see, when it is the fast dissociation, that is the first dissociation, this is the second dissociation, right? So for the first dissociation, this dissociation tendency is always high. Whenever you will have more than one hydrogen that can dissociate. So always remember, if you have any acid and there is more than one basicity, that is number of H plus can be, you can get from a single molecule of acid. If it is 2, 3, 4 like this, then obviously the first dissociation is maximum. So that means when you will reach this species, HPO4 2 minus, it can also act as acid. How? Because there is one more H is left for dissociation, and it will produce H plus and PO4 3 minus, right? So this can act as acid, the first dissociation. This is a third dissociation. That means this is also acid and this is also acid, because all of these species can, they are able to give some H plus. But not just able is not enough. What is their tendency? How fast they can give, that also you have to check. So HCl and HNO3, obviously these two will not be our correct answer. Now you are stuck between these three because all are related to same type of compound. So H3, among these three species, B, C, D, H3PO4 will be maximum acidic. And once you have reached this H2PO4, then it is also acid. Now it is better acid than option D species. So option D species will be the weakest acid among B, C, D, because A and E we have already cancelled, right? But B, C, D, among these three, the last species, that is the last H plus, when it is dissociated, this tendency will be very, very weak, because already it has given 2 H plus. The last species already carrying some negative charge. The last H plus donating tendency is very, it is minimum. That is the reason option D will be the weakest acid. It is the, among these, it is the probably the weakest acid. Now we will have the discussion general preparation method of acid. So the first method, as you are seeing here, direct combination of elements. So it is a synthetic method where we are preparing here, the example that you are seeing here, we are preparing HCl, hydrochloric acid, very common acid, So when we are preparing it, then we are starting from the elements. So two elements are there, hydrogen and chlorine. So the elemental state, see, we have here hydrogen and chlorine in their elemental state. Hydrogen is gas and chlorine, that will be basically, you can also consider it as gas. Mostly it is as gas. And HCl is also gas. But if you are thinking that how HCl can be gas, it should be aqueous. Normally, when there is formation of HCl, it is not liquid at all. It is G. The physical state is gas. But when you mixed it with water, then you have some HCl solution. So if you are seeing any HCl solution in bottle, in any container, that is basically it is mixed with water. The gas is mixed with water. Then you are having the HCl solution. So HCl, if it is mentioned within bracket G, it is okay. So in this method, we are directly combining the elements that are present in this acid. The second method is by the reaction between an acidic oxide or non-metal and water. So acidic oxide of a non-metal, or you can say oxide of a non-metal. Acidic oxide or oxide of a non-metal. Both are actually the same thing. When you have any oxide, that is oxygen compound, if the other element is non-metal, so here look at this, the other element is sulfur, other element is phosphorus. So these two oxides both are the combination of some non-metal and oxygen, non-metal sulfur, non-metal phosphorus. So when you have some oxygen compound of a non-metal, it is, that is oxide of a non-metal, it will behave as acidic oxide. So whether you say non-metallic oxide or acidic oxide, it is actually the same thing. So here we have taken the acidic oxide, sulfur dioxide, we are combining it with water, and there is formation of acid, sulfurous acid, H2SO3. Similarly, we have taken an oxide of P4O10, oxide of phosphorus, which is P4O10. There is another oxide which is P2O5, which is the monomer of P2O10. If you double this, you will get the dimer, which is P4O10. So P4O10, when reacting with water, there is formation of HPO3 acid, right? So there are different types of phosphorus related acid. So HPO3, this is another acid. In the previous example, you have seen H3PO3, but now you are seeing here HPO3. So there is also H3PO3, then H3PO2, different species are there. Okay. So these are the two methods where we have taken some non-metal and we have taken water. Next method, displacement of weak. Let me check the oxygen whether it is correct or not. Okay, this is fine. Displacement of a weaker or more volatile acid from its salt by a stronger or less volatile acid. So what is the meaning of this statement? The meaning is, look at this equation. We have taken sodium chloride salt and acid H2SO4. We are having product side hydrochloric acid and NaHSO4, right? That means one of this H is replaced by Na and that H is combining with Cl and it is producing HCl. So here if you compare H2SO4 and HCl, HCl is more volatile than H2SO4. More volatile. So here we are preparing a more volatile acid from a less volatile acid. So this one is less volatile acid. So we are starting from H2SO4, which is less volatile, and we are having a product which is more volatile acid. You cannot do the reverse because when you will try to do the reaction, that is, it is not so stable. It will be, that is, as it is having volatile nature, you will not be able to do the reaction. So only this direction it is possible. So we have taken a less volatile acid and we have taken a salt which is containing the anion of the acid which we are trying to make. So you are trying to make HCl, which is containing chloride ion. That ion must be present in the salt, which is NaCl. Similarly, here we have another reaction, though it will be a little difficult for you to understand because the actual structure of Na2B47 for this grade it is not required. But just try to understand the reaction. H2SO4. Again, we have taken a less volatile acid. We are trying to make a more volatile acid. H3BO3 is this type of formula. Boron attached with 3OH group. So for formation of H3BO3, we are starting from a salt, which is salt of that must be having this boron. So we have taken a salt of boron, and here we are preparing H3BO3. It is easier to understand with the previous example, but here also just if you follow the acid, which acid you are using in the reactant side, which acid you are getting in the product side, these two are more important. So here this salt is containing sodium plus ion, and rest of the ion, it is a little complex structure, so I'm not going into the details, but it is a salt of boron. That is the anionic part of this acid. That anion is present in this Na2B407. So same concept, we are using some less volatile acid, and in the right hand side we are getting more volatile acid. And the last method, displacement of insoluble sulfide from a metallic salt by hydrogen sulfide. So this is hydrogen sulfide. Here we have, this is the metallic salt from a metallic salt, Pb CH3COO whole 2. Now CH3, if I am writing its structure, it is actually like this: CH3 C double bond O, then COOH. Now this acid, when it dissociates, it is having the ion CH3 COO, C double bond O, O negative. Now this is called as acetate ion. Now if this ion is attached to lead, lead is having 2 positive charge. That means if it is lead 2 plus, there will be 2 acetate ion attached to it, right? Whether you write like this or this, same thing. So 2 negative charge balanced by 2 plus. So this is the structure of lead acetate. So what we are doing here, this lead acetate, we are removing these 2 acetate anion, and these 2 anions are combining with 2H plus, and this sulfide, here it is 2H plus and sulfide S2 negative. So this sulfide is now captured by Pb2 plus, and we are getting PbS. So this is the displacement of insoluble sulfide, as if we have displaced this Pb from lead acetate, and now it is connected to sulfide. And this is insoluble. Look at this. Physical state is mentioned as solid. That means it will be precipitated in the medium, and you can get the acid easily. Separation will be easier. So we have here replaced this acetate ion, or you can say we are replacing the Pb, and now it is attached to sulfide, and H plus is now attached to acetate ion, and we are getting acetic acid. So these are the 4 methods for the that is the preparation, different methods for acid, right? Now what about base? First method, burning metals in oxygen. Suppose you have taken some metals and you are burning it in oxygen. Then there will be formation of metal oxide. Now it is true that in this it is metal oxide. Remember, when there is some metal oxide, it will be basic in nature. Just like non-metallic oxide, SO2, CO2, they are acidic oxide. So when it is metal oxide, it will be basic oxide. So they are basic in nature. So from that definition, you can say that is it is true that there is no OH hydroxyl ion, but that is not always necessary. The compound can be basic in some other way also. So sodium oxide and MgO, they are basic in nature, so you can consider this equation as if they are preparation method for bases. So MgO, though it is solid, but when you take its water solution, it will be converted to hydroxide. Similarly, Na2O, when you take in water, it will be converted to NaOH. So ultimately they will be base. So that is the reason you can call them base. Second method, adding water to metal oxide. Now see what we have done. If you are having any problem to define it as base, now look at this. This compound, when you are adding water to it, there is a formation of NaOH, that is sodium hydroxide, right? So Na2O reacting with water, there will be formation of sodium hydroxide. Similarly, if you start with another metal oxide, which is calcium oxide, then there will be formation of calcium hydroxide. So calcium oxide Na2O, they are solid compound. You can think that they are how they can be base. But these metal oxides, when they react with water, ultimately they form base, which where you can see hydroxyl ions, right? So next we'll have which, sorry, there is the third method. Will be not there. So it is now balanced, right? 2 hydrogen, 2 oxygen. Okay. Third method is by the action of water or steam on some active metals. Active metals means there are different types of metals actually. So when you will see in the periodic table, the metals that are present in the left hand side, that is in the S block, they are very active metals. They are very reactive. Not just S block, there are some metals in the middle portion also, D block, they are active metals. So active metals like sodium, potassium, they are very good example for active metals. So they even can react with cold water to form hydroxide. So see, we have taken sodium and water. So sodium in this equation, you have seen how they are reacting with oxygen, but now they are reacting with water, and we are getting sodium hydroxide and hydrogen gas, right? Now, instead of taking active metal, suppose you have started with magnesium. Now, I am now saying this is not active, but it is not so strong like sodium. Sodium is from group 1, but magnesium is from the next group, which is comparatively less reactive. That is why magnesium cannot react with cold water. You have to increase the temperature. It can react with steam. That means now the temperature is high. Now, it is forming magnesium oxide. It is not MgOH2, but see, this is metal oxide. Ultimately, you can convert it to MgOH2. So that is why it is also base. By heating carbonates of some metal. So CaCO3 is calcium carbonate, and when you are heating it, there is formation of this base and CO2 gas by the action of alkali on a salt solution. So this is a salt. Details of salt we'll discuss next in the later part of this unit. But if this is salt, you are treating it with an alkali and you are getting another alkali. Just in the previous slide you have seen preparation method for acid. You are using H2SO4 to generate HCl. Same thing also you can do here. NaOH is more reactive than MgOH2. So it will react better with MgSO4. It will form these two. Now reverse reaction you cannot expect because MgOH2 is comparatively stable than NaOH. So it can remain in the product side. But as this is more reactive than MgOH2, it will be in the reactant side. Ultimately it is producing MgOH2. So Mg and OH together, SO4 and Na together. So this is the end of general preparation method of acid and bases. Next class we will see their chemical properties. We are at the end of the session. Thank you for listening.